start lecture 7, and the course is corrosion protection methods. And today's topic will continue the corrosion protection using design or geometry aspect. Now, and the subtopic for today's class are, so one is failures that are encountered due to a faulty design. And the second one is the rules or the guidelines for designing component. And both are towards corrosion protection. So, that means once we know failures due to design aspect, we can actually find out or formulate rules as well as guidelines for designing components. Now, if we look at our previous lecture, lecture 6, we have talked about several factors which can influence design. And while discussing that, in fact, we talked about some of the failures that can happen. Now, if we list down those failures, some of the failures, it is not all, we are just listing down some failures due to faulty design. Rather, I would say this, let us put it as failures that can happen in the context of design. And we are talking about metallic components. Now, there could be possibility of overload, and mainly control instrumentation or operation, if there are overloads, that can lead to failures. So, overload, weakening effect on plant control instrumentation or operation. So, overload could be stress overload, workload overload, or there could be possibility of electrical overload, all those kind of stuff that can have weakening effect. Second is, there could be abnormal situations or conditions. Abnormal situations like catastrophic failure. Okay, so that is abnormal situation, and that can happen if we don't use, not using compatible alloy parts or metal parts. So, that means we are not making galvanically compatible metal parts. There could be possibility of overload of chemical inhibitors, or if the inhibitor content is not properly checked or the inspection is inadequate, those cases we can have abnormal situations like inadequate inspection, it falls under control part or control. Okay. There could be problem like poor fabrication leading to failure of component, and that can, because poor fabrication, what are the poor fabrications? Like if we have excessive cold work, flame hardening, if we have a wrong flame hardening operation, or if we have excessive torque or excessive mechanical loading, those can lead to a difference in stress in the material, difference in residual stress. For example, this can introduce residual stress. Even this can introduce residual stress. Excessive mechanical loading can introduce residual stress. So, those are coming due to poor fabrication and even machining. So, if we do not have a proper machining, means the amount of machining that is required to maintain the matching surfaces or the surface smoothness or surface texture, then we can have problem. Okay. Then poor handling, this is a problem. Then there could be scratches, poor handling can lead to scratch, and that scratch can generate pitting, that scratch can generate stresses. So, those can lead to early corrosion failure. And we have talked about this in the previous lecture also. The inspection, the scratch and inspection is, these two things are seriously related. Time to time we have to see a part and then see that whether the operation led to some serious scratch marks on the material, and that scratch mark can lead to a stress corrosion cracking or corrosion fatigue. All sort of problems can generate. So, that comes from the poor handling or poor inspection. Then there could be incorrect assembly. Incorrect assembly. So, what is this incorrect assembly? And those are coming in the joining section. So, again that compatibility issue will come. So, for example, welds or rivet or bolt, all those cases, if we do not carefully observe how to do it, and if it is not properly done, and if there are portions which are possible corrosion attack portion, so we have to be careful those cases. And in fact, if we do wrong fitting, let us say bolting is done without having a proper match between these two parts which are to be bolted, there could be stress in the bolt, and if that particular segment is exposed to the corrosive, because of that stress generation, the material can have stress corrosion cracking. Similarly, for example, if we have a weld, let us say I weld these two parts, okay, for example, rivet. So, this is the rivet, this is the rivet, we are joining two parts, this is one part, this is another part, okay, this is another part. Now, incorrect assembly means if this rivet has a stress, a shear stress existing. So, then the rivet can bend like this. Rivet can bend like this, and if this rivet bent is exposed to corrosive, definitely stress corrosion is one of the failure paths. We have to be careful there. And in fact, another part we have to be careful is the rivet material as well as those two segments which are to be fastened, their material should be as close as possible in the galvanic series. And even if that is not possible, there should be proper insulation between two different materials. So, we will talk about that part in greater details when we see some of the case studies and some of the examples. Then we can have problem related to storage and transportation. We have discussed in the previous lecture also, as I was telling that storage is important as well as transportation. So, you just look back in our previous lecture. Storage means we have to see that whether the material is properly sealed, or the stacking should be done, that during transportation there must not be much of mechanical abrasion between two subsequent layers. So, those kind of issues are to be taken care of, as well as they should be properly tightly held, so that the material cannot, because of those jerking in the transportation vehicle, those materials should not displace to a great extent. More importantly, sometimes we have to take care of the fretting. Okay, fretting corrosion is a problem when transportation happens. So, if you say two big metal objects are placed one above another, and during movement, if there is a little bit of fretting movement, see, there will be a fretting action at the interface, because one is on top of another. So, there is a load falling on top of the bottom layer, bottom part of the object, as well as of the top object. The interface is getting that stress, and if there is a very small amount of sliding movement, then there could be a possibility of fretting corrosion. So, we have to also make sure that those kind of situations are properly tackled. That means proper insulation is done, proper holding is done, fretting action can be tackled quite efficiently. All those things are to be considered. For example, transportation, let us say the long distance transportation, then we have to be careful in storage part. That means, just when the material is transported from one place to another, and because of the transportation, when it transports from one end to another, if it goes to a different environments like dry environment, wet environment, sea water environment, all those kind of stuffs will lead to have different effects on those materials. So, the material should have a proper sealing, proper protection routes, like water absorbing ability of the water absorbing materials to be kept in that pack. All those kind of stuff are to be taken care of. Now, then of course, accessibility. So, this accessibility, it actually indicates that how to do easy repair. Many a times we have to actually do inspection and see that whether some corrosion has taken place at some portion. So, we should be able to access that portion easily, and we can take remedial action. So, that is what the design should be, such that accessibility is better. Otherwise, we will be protecting around that zone where the severe corrosion is taking place, rather than ignoring that part which is to be tackled in the beginning. So, that would lead to later on it can also lead to a serious failure of that component. So, accessibility is very important part, which is also related to the inspection and control. So, it is also related to inspection, control, as well as finding or funding remedial action. Okay. So, these several failures can happen because of these problems. These are the issues which can be possible, and all are related to a corrosion related failure. And if you see, these points to some extent are related to a great extent are related to the factors which are important to influence design. The previous lecture if you see and this lecture if you see, you will see quite a lot of continuity, that is there. Okay. Now, so once we know factors which influence design, now once we know failures that can happen due to in the context of design, we should be able to see what are the guidelines for a better design. So, the guidelines for better design so if we note down, then you would see that while discussing those factors as well as failures, we also touched upon some of the guidelines. Now, first guideline that we can think of, the tank design. It should be such that the proper drainage is possible, then most of the times if we have a tank, bottom venting system, and then it should have design rounded corner, why rounded corner? It actually avoids crevice. So, wherever you see crevice, you just try to make it rounded. Then there should be slope at the bottom towards the vent or pipe. Okay. And another important part is we should be able to clean easily. So, cleaning is required. That why? Because whatever tank you design, let us say potable water tank, there will always be some deposit at the bottom. So, we should be able to clean that properly, quickly, and that is what this slope, if you see these two parts, the slopes will be helpful towards the vent, and at the same time it should be such that there should not be any unnecessary water retention. Water accumulation. Okay. And in fact, if you see, we have actually talked about it in our first few lectures. So, we will talk more on this. One such design we talked is basically like this. Isn't it? So, the sedimentation, this is inlet, this is outlet, and these are the cornered part where it is rounded, because it is avoiding crevice. So, initial design, if you have this design, this was the initial design we thought of. This was the initial design, and from there this modification has happened. And if you see, all points are incorporated there. Let us see one by one. If we consider this corner, which is crevice, so this is now rounded, crevice is out. Then there is a possibility of deposit, and it is a difficulty to take those deposit out easily. If it is a big tank, one has to tilt, and that tilting is not possible. Small tank, still it is possible, but still you will see that some amount of deposit will stay back. It is impossible to take away all the deposits because of this design. Now, if it is a big tank, only up to this much, up to this particular lower part of that exit, we can take out water, but some water oil always will be retained there. So, water retention is a problem. Fine. Now, if you have this, you have flow all the time towards this, and that will actually allow those dust particles along with the water to go out. And since there will be a flow, because here if you see, the flow is like this. Fine. So, flow is this way and then this way. This is outlet. Okay. Now, if you see that corner, this corner, not much of flow is possible, because that corners are away from this flow region. So, there will be stagnancy. So, it will further enhance the crevice formation. But here we will always have flow, there will be no dead zone or the stagnant zone. At the same time, this debris can also go along with this water flow. So, that means we are making, and at the same time we are not going to get this water retention. There will be always a proper drainage. The proper drainage is maintained, bottom venting system, rounded corner, slope at the bottom towards the vent. If you see, the slope is towards the vent. It can easily clean. It can also avoid unnecessary water accumulation. So, avoiding, so this is avoid. Okay. So, this is about the tank design. These are some of the guidelines for designing of tank. I am not talking about the materials part. Okay. So, that material aspect also should be considered. Material aspect. So, this material aspect, here we are considering all materials are same materials. So, that means a proper compatible material is maintained. We can say compatible material. Compatible material means, if we see galvanic series, let us say M1 and M2 as well as M3, these three materials are there, from which I have to choose that material for the tank as well as pipeline system. So, then let us say this M3 is closer to M1. It is better to choose these two rather than this or this, because these two are closely spaced in the galvanic series. So, that means galvanic effect will be minimum there. There will be galvanic effect if we have M1. So, that means if we make a circuit M1 and M2, these two metal in the electrolyte, and let us say we are connecting this with a conductor in the electrolyte, this will be anode, this will be cathode. Okay. Now, current will flow through this. So, M2 would try to dissolve and M1 will be protected, but that degree of this kind of corrosion of M2 would be very less. So, that material best would be the same material. So, if we can use the same material, this will be the best, and then this is the better, and these two are no, that means they are not compatible in the galvanic coupling mode. Then second part which is coming is weld. Weld is better than rivet or bolt. And even if riveting and bolting is done, we should be able to weld some of the portion where crevice is possible. And when we weld that weld thing, weld materials, there also this compatibility has to be looked at. Okay. Compatibility, here compatibility all the time, remember we are talking about galvanic compatibility. Okay. So, we will talk about this with different examples. For example, if we consider the rivet part, this is the rivet, so these two plates are riveted, and if you see these two plates, there could be a possibility of gap, and that gap can lead to crevice and again crevice corrosion. So, it is better that we put weld here, compatible metal weld, and this part is also welded, the center part is also welded. So, that means what we are doing, though we are doing rivet, but still we are using weld to close down those crevice openings. Otherwise, there could have been problem here, there could have been crevice corrosion here, crevice corrosion here, even inside it can ingress through the small gap, there could be crevice corrosion in those portions also. So, these are all corrosion points. Fine. So, that means it is, but if we do welding, it has an advantage. Like let us say if you are doing welding, let us say one block is welded like this. If we see this weld part, so this part is welded here. So, when we do welding, after doing welding, so this is the weld part. So, now if we see this shape from this particular direction, if we look at, so it will be like this. This will be the look. Now, this particular portion, these are two crevice part. So, we have to avoid that crevice. So, what we can do, we can put little extra weld here and make it rounded. Even we can also, after the welding, we can also do little bit of grinding also. So, that actually remove crevice. So, now there is no gap since it is a continuous weld, as well as we have also tackled the crevice part also. But now, had it been spot welded, let us say we are doing a spot welding. So, this 3 places, the green colors are basically let us say spot weld, then it will be a problem, because since it is not completely covered with the weld material, we are having gap here. And those gaps are again susceptible to crevice attack. So, but if we do weld also, the riveting is a problem. This is one such problem, that after riveting we should not leave any gap between these two matching surface, and that is what weld would be better. But while doing welding, we should choose a better welding method depending on the situations. We should not leave any crevice or gap there, and at the same time we should not leave any cornered part. We will talk more on this particular issue, the welding and riveting and bolt, what sort of problems that can arise, and those problems can lead to a corrosion related damage. We will have a lot more examples on that. So, we started talking about guidelines for better design, and we could cover 2 in this particular lecture. We will continue on these guidelines for better design in our next lecture also, and then subsequently we have specific examples on all those guidelines based situations. So, all those discussion what we had today, those are actually if you follow these 2 source material, you can get it. The one source material is corrosion, ASM handbook, volume 13A, and the second one is corrosion engineering. This is a book by Fontana and Green. By M.G. Fontana and N.D. Green. Okay, this is a book published by McGraw-Hill, New York. Okay. So, these 2 source material you can refer to get whatever we have discussed. In fact, there it is written in a very short manner. We have discussed lot. So, let us stop here. We will continue our discussion in our subsequent lectures. We have just covered 2 design aspects, the guidelines for design. We have lot more to discuss, and we will do it in the next class. Thank you.